So we briefly mentioned perfect sets. Just recall, a set is perfect as long as it's the empty set, or the set is closed and every point in that set is a limit point of the set. So simple example, we'll take Q. Q is not perfect subset of R. Do you remember why? Well, what's wrong? Q is not closed. But Q is a perfect subset relative to itself. Why? Because, well, relative to itself, the space is closed. And it is true that every point in R is a limit point of R. In particular, every point of Q is a limit point. Well, every point in R will be a limit point of Q, so therefore every point in Q is a limit point of Q. Rationals are everywhere. They are dense in the real number line. That's the phrase we will talk about. Okay? So then we briefly try to characterize the subsets of R. What can be said? Of perfect subsets of R. Well, one thing that we mentioned, I'm not sure if you followed the reasoning, do you remember that in terms of cardinality, all perfect subsets of R have what sort of cardinality? All perfect subsets of R, I should say non-empty. Perfect subsets of R are uncountable. So that's a pretty useful tool. You'll be able to prove many things that will come easily if you understand the statement. Do you understand how I know that every perfect subset of R is uncountable? Notice, look at this example. Q is countable and Q is a perfect subset of itself. So it's not true about perfect sets in general, but if you are dealing with the real number line, no countable set other than the empty set can be perfect. Now, why is that the case? So, recall, if P, a subset of R, is countable, I can form a nested sequence. I can form, that's what R has. I can form a sequence of the form x n of 1, x n of 2, and inside of it I will be able to select another sequence, another interval x n of 3, x n of 4, etc., such that the length of x n k to x n k plus 1 goes to 0. Okay, so I can create a nested sequence. So what I mean is, assume that that I can say P is countable. So it's the form. It's of the form xn, where n goes from 1 to infinity. All right, so if it is countable, what I can begin doing, I can select one point of that perfect set, and obviously it cannot be just the only point, because it must be a limit point, so there must be at least one other, okay? So let's select, let's say, one point, that's why I call it xn sub 1. Whatever that point, it may be the millionth point. It may be in this list, it's the millionth point, okay? And then I know that no matter how close I come to this point, I can select an interval around this point. It's a limit point. Okay, so that means that somewhere near this point, let's say to the right of this point, or to the left, doesn't matter, I can select another point xn sub 2. And that's a point of the perfect set, and the distance is less than 1, let's say. Okay? Now, in this interval, a bunch of points might still persist, but then what I can do is I can shrink the interval to exclude both endpoints. I can then, inside of this interval, there must be other endpoints. I eliminate the left and right points, and I shrink the interval. And if you describe it, if you think about it, describe it precisely, you will see that you will eliminate all the points that you have counted. Does it make sense? You see, do you understand the algorithm, right? The algorithm is to look at a point. You pick a point, and then zoom in, close the interval from the side where it has limit points. So that basically the interval that you closed contains infinitely many points. Okay, and you zoomed in until the size of the interval is really small. Good. So a bunch of points were eliminated, maybe x1, x2, x3. So basically a bunch of points are not in this interval, perhaps. So what you do is you eliminate the left and rightmost point by selecting two other points. Each of them have the limit point within this interval. So you eliminated those at the edge and possibly more. Then you eliminate the new edge and possibly more. And at the end of the day, you must have, if you do it carefully, you will eliminate all the points in the list, and therefore it could not be countable because the sequence must actually converge, right? So this nested interval sequence will actually have to equal to a single point x, which is not a point listed. So this is a point of P because it's the limit point of the left endpoints or the right endpoints, and it was not listed. Did that make sense? I'm not sure if I did. So we have a few more definitions. So we state that a set A, which is a part of a metric space, is dense if the closure of the set is the full space M. So you can say dense, the word is dense in M. So you say usually A is dense in M. So what does this definition mean? It means that every point in M is either a point in A or a limit point of A. Okay? So a good example is Q. Q is dense in R. Why? Because either you already have a rational number, or if it's irrational, it's the limit point of rationals. So if you take the closure of Q within R, you get the whole of R. So let's put it as an example. So Q and R throw away Q are both dense. In R. Okay? And well, B, let's say if M is discrete. If M is discrete, the only dense subsets are, well, what are the dense subsets of a discrete space? Only one thing is possible. All right, good. So I know you don't understand anything I'm saying. Well, at least we established that. Let's see where we stop. So let's look at this example. M is discrete. Discrete means that if you take a point, you can select a neighborhood that only contains that one point, right? Just take X in M, and if you take radius of the ball to be equal to 1, then that ball will contain only that one point. So what does it mean for a set to be dense? So if I have A, a subset of M that is dense in M, what does it mean? It means that every point that I look in M is either already a member of A, or it is very close to members of A. It's surrounded by A. Right? A either touches a point in M, or that point is already part of A. Make sense? So in a discrete space, what are the only dense subsets? So I have a discrete space, I take a subset A, and A must have the property that either the point is in M is in A, or A is arbitrarily close to that point. What is that subspace? Did I make a mistake with the exam? I think I did.
Is it M? The null set?
Yes, M. No, null set is not dense. Null set, its closure is not going to be M, right? R, M itself. Make sense or not?
If you're looking at if R is dense, will the set of limit points be uncountable?
No, we're confusing things now. All right, a lot of confusions, and I guess maybe my fault. I rolled whatever this thing is, and I'm waving my hands. I look into your eyes; they express nothing to me. But then I have other worries. So, perfect set. Do you understand what perfect means? Perfect means the set is closed, and every point of that set, of the set P, is a limit point. Not only is it closed, it's a limit point. So imagine a party. So in a great party, no one is standing alone. Nobody is isolated, right? So everybody has friends that surround him. So a perfect set is like a party, exclusive party. Nobody that is not supposed to be there is at the party. And everybody at the party is surrounded by friends. That's a perfect set. Do you understand what I mean? So it's an exclusive club. So in other words, some stray person, they will not surround him, right? They are exclusive. They don't like members of, basically it's like a yacht club, right? Of millionaires, and each millionaire has many millionaire friends. So you look at a millionaire, you draw a circle around him, and no matter how small the circle, there are going to be other millionaires that are yacht owners right next to him, okay? And if you pick any other person that is not a yacht owner, millionaire, he is not surrounded by those people. They're not next to him. That's a perfect set. You see the analogy? What is a dense set? A dense set is not like that at all. It's much more democratic. What is a dense set? What does it do? So if a set is dense, what it does, it actually is, so every member of the set, basically every member of the entire universe of points is either a member of the set or is surrounded by members of the set. That's a dense set. Okay? Does it make sense? I'll give you some intuitive examples in a moment, because it's going to be more confusing. Now I'm going to talk about nowhere dense sets. Or everywhere, so there's an everywhere dense set, nowhere dense set, and not dense. Okay? Only terminology. You see, that's not a lot of difficult ideas. It's just basic terminology. But, can you see this terminology? So I'll make this definition, and then we'll try to play a game. Maybe you will understand it better. Definition. So a set is said to be nowhere dense is nowhere dense if once you take the closure of the set and then you take the interior, then you get the empty set. That's what nowhere dense set is. So let's try to see basic examples. So here's our favorite example is, let's say, 1 over n. Take the sequence 1 over n. Is it dense in R? And then is it nowhere dense? So let's ask this first. Okay, is it dense in R? Let's stop here. Is 1 over n a dense subset of R? So what does it mean? What I'm asking is, it's a primitive question. So here you have the point 1. Here you have the point 1/2, then 1/3, etc. Right? So is this a dense set of R? Yes? Oh, obviously it's dense. Yes? Shake your heads, for sure. Okay, you know nothing about what I was explaining. Wonderful. What is a dense set? A dense set of R will be what? So you have what are the members of the set? 1, 1/2, 1/3. Is 5 over 7 a member of the set? The set is 1 over n for each integer 1, 2, 3, 4. Is 7 over 5, is it a member of the set? No. Is root of 2 a member of the set? No. Is minus 3 a member of the set? No. So you know at least membership to the set. You know who belongs in that set. Okay? Now I'm asking, is it a dense set of R? What am I asking? Could anybody try to explain to me? So you know which elements don't belong to that set. So if I'm asking, is it dense in R, I'm asking, well, if you pick a body that is, a number that is not part of this sequence, so pick, for example, -1. -1 is not a member of the set. If this were a dense set, it would have to be what? It would have to be a limit point of the set. In other words, it would have to be arbitrarily close to numbers of the form 1 over n. Is it true about -1? No. So you can pick plenty of numbers, and they are not limit points of the sequence, and they are not part of the sequence, and therefore the set is not dense. So the answer, and here is how you do it by closure. So answer. So you take 1 over n, and you take the closure, and what do you get if you take the closure of 1 over n? You just get 0 together with the sequence 1 over n for n equal 1 to infinity. Okay? So with the closure you get 0, and the closure does not give you r. So the answer is no. 1 over n is not a dense subset of R. Okay? It's not a subset of R. Now I'm going to ask about the same 1 over n. And I mean the usual metric. Is it dense in itself? Or relative to itself? Is it dense relative to itself? Simple question. The universe, what do I mean relative to itself? Now the universe is nothing but 1, 1/2, 1/3, etc. That's my full universe. Is the set dense in its own universe? Yes, why? Trivially, because you cannot pick a point that is not a member of the club. Okay, remember what dense set means. Very simply, it's a dense set. Let's call it a club, right? So it's a type of club where basically every member that is every non-club member is surrounded by by people from this club, right? So maybe a dense set is a set of religious zealots, right? So if somebody is not of that religion, they are right next to him, right at his throat, to try to convert him. I'm not sure if it helps you, but visualize it, right? So R is, well, the sequence 1 over n is not dense in R because there are plenty of real numbers that are not approached by members from that sequence. Okay? So therefore, mathematically, the closure of the set does not capture everything. Okay? But if you were to take Q, what's true about Q? So either it's a rational number, or if you take, let's say, root of 2 will be arbitrarily close to rational numbers. So every point is either a limit point or a member of the set. Could be both. But basically, if it's not a member of the club, it is the limit point of that club. So R is dense relative to itself. Now, next question is, so the answer is yes. And you should understand why. So another question is, so if I take 1 over n, is it nowhere dense? Dense in R? That's the question. Is it nowhere dense in R? Now, nowhere dense means that that it is not. It is so sparse. So look at what we do. We take the closure and then we take the interior. So the question is it populated enough? That nowhere dense set means it's not populated enough to even approach creating its own neighborhood, right? So even if you were to feed the limit points to that set, it still does not have any neighborhood. So right, not mathematics. I'm just talking about. It's really just a lexicon. A lot of the things that we do is no more than lexicon. Just understanding the terms nowhere dense, etc. Not even difficult ideas. So is 1 over n nowhere dense? Any ideas? set nowhere dense. What do you think? All you have to do, again, let's say right now you have no clue what I'm asking. You just take the closure and you take the interior. This we did. Take the closure and then take the interior. What do we get? So we take 1 over n closure. And then we take the interior. What do we get? What's the closure of 1 over n? 0 is the point we add. So the closure is the set together with 0. What's the interior of that? All right. What's the closure of 1 over n? One person says, take the sequence and add 0. I'm just thinking, should I tie you to a chair and begin interrogating you now? I have a feeling that you're going to be partisans. You're going to be brave partisans. I'm not going to tell you. Right? What's the closure? I'm not going to tell you. What is the closure of the set? What is the closure of 1 over n?
It's the set itself with 0.
It's the set itself with 0. Do you understand why? What's closure? What does closure do? You take the set and you add up limit points, goddammit. You add up the limit points. Do you understand what I mean, right? 1 over n. What does it touch? Does it touch any points? It touches 0, yes? Does it touch 0? Does it touch 0? I'm going to bring the pliers. Does 1 over n touch 0? The sequence. What do I mean by that? Take 0, take a neighborhood around 0, no matter how small the neighborhood around 0. Let's say I took a neighborhood small around 0. Does this neighborhood contain points of the form 1 divided by n? Yes, so that means that 0 is touched by the sequence. That's what I mean by touching, right? So they are arbitrarily close. So 0 is included. Anything else is included? No. Take any other point, let's say the points 1, 1/2, they are all separated from one another, correct? So no point 1/2, 1/3, or etc. are limit points of that sequence, correct? And if I take any point, look at it, just you can even imagine it on a number line. Take a point anywhere that between those numbers other than 0, I can select a tiny interval that will not contain any points of the form 1 over n. So it means that other than 0, nothing is added. So what do we get? We get 0 union 1 over n. And then I take the interior of that. What's the interior? What are the open subsets of this? You remember how you see what subset is open. So you look into that set, you pick a point. The point is in the interior. If I find a full neighborhood, full open interval in this case, that is part of the set. Do I ever find something like this? No. So what is the interior? Is 1 in the interior of the set. Remember, this is the sequence. 1, 1/2, 1/3, and then 0 is added. Is 1 in the interior of the set? Why not? Because I can take a neighborhood like this, no matter how small it is, it's not, this neighborhood is not entirely contained in that set. Remember, the set is 1, 1/2, 1/3, and then 0. So 1 is not in the interior, yes? Is 1/2 in the interior? Select radius to be a distance less than 1/2 minus a third, and then you'll see that 1/2 is isolated. And every interval containing 1/2 will not be able to contain any other point. So therefore 1/2 is not in the interior. Is 1/3 in the interior? No. Is any point in the interior? No. So the interior is empty. Even simpler, this set is countable. I just have countable infinity plus 1 is still a countable infinity, yes? Could a countable set ever have non-empty interior? If a set is countable in R, can it have non-empty interior? Remember, interior means you contain at least a full interval. The set must contain a full interval. But any interval of the form x minus epsilon, x plus epsilon, this is I haven't really used that word often, but it's identical in a sense to the interval from 0 to 1. So how many points are contained in an interval? Uncountably many. So therefore, if a set is countable, automatically it cannot possibly have non-empty interior. Again, be careful. If the distance is as we measure, if the open sets as we measure. The open balls in R are just open intervals. Each open interval is the same cardinality as the interval from 0 to 1, which is uncountable. So without thinking, I know the interior must be empty. So this set is nowhere dense. All right. I will try to illustrate the ideas here. So, one question that I want you to try to answer: if a set is not dense, so some set is not dense, can I conclude it's nowhere dense? A set is not dense. What does it mean for a set not to be dense?
Might have like a stray point somewhere else.
Right. A set is not dense if what? If there is a point that is not part of the set, which the set is not touching. You understand what dense means? You have the property that you touch every single point that is not a member of the set. So what are dense sets? You can imagine like a club of religious zealots. So they don't need to convert themselves, they're already converted, but everybody who is not converted, they are like at his throat. Okay? So that's what a dense set is. Everything is either a limit point of that set within the universe, or it's already part of the set. So so for a set to be not dense, if you have a single point that is escaping, that is not surrounded, let's say not part of that set and not surrounded by it, then you can say it's not dense. Is it the same as saying nowhere dense? No. Alright, so here is an example. So you have sets that might be said to be locally dense. So for example, you can go to Brighton Beach, right? If you go to Brighton Beach, what do you find? You find that every single person on Brighton Beach is either a Russian or is surrounded by Russians. Right? Just Russians are right next, right? So what does it mean? It means that locally within the neighborhood of Brighton, within that neighborhood, you have that property of denseness. But if you move somewhere else, if you move to Manhattan, that property fails, right? So you can find people that are not surrounded by Russians. Good?
You're telling my life story.
Your life story? Where do you live at Brighton?
And now you moved to Manhattan, that's it.
Well, yes. So do you understand? So the Russians are not dense; they are locally dense in the neighborhood of Brighton. So if you restrict your universe to be Brighton, then you say the set of Russians is dense there, because everybody is either Russian or everybody that's not Russian is right next to one. So you can draw a circle around him, and right next to him there will be a Russian standing. Okay, good. Now take the Germans, for example. So Germans are a set that is in New York. If you take all the points in New York, it's a nowhere dense set because it's very hard to find them. There is no place where you find that that has this property. There is not even a neighborhood of them. You understand? So here is another example. I'm hoping it illustrates. The concepts are extremely simple. Extremely simple. So sorry for being whimsical, but right, was done a while ago. So you watch movies, I suppose, right? And you have those silly movies about zombies. So what you have is here you have the red dots. It's basically what HQ sees on the screen. Those are the special forces. Okay, the red points are the special forces. Here is the escape helicopter, and everything here is basically the set of zombies. Okay. So let's try to understand which set here is dense. So basically, we consider points to be every black or red dot on the paper. Okay. So let's ask. Okay, the set of zombies, is it a dense set in that space? Remember, the space is only the points drawn, either red or black. So the set of black dots, is it a dense space? Z, right? Z is a subset of M. M is the set of all red and black points. Z, is it a dense subset of M? And the answer is, based on the picture, and please tell me why do you reason this way? Anybody? Yes, please.
Because it's either zombies or things that are close to zombies.
Exactly, right? So they're like zealots, right? Either a point is black, and we don't need to worry about whether it's a limit point or not. Like you see, here is a point that's not a limit point, here is another, it's not a limit point. Doesn't matter, they're already members of Z. But what you see here is, if I take a point that is not member of Z, then it's then no matter how small the neighborhood I draw around this point, then that neighborhood will contain plenty of zombies, right? So that means that the red points are limit points of the black ones. Good? So Z is a dense subspace of this M. Make sense? Now let me ask you another question. Now let's look at the red points, right? So the red points is the set S, special forces. What can you say about them? What, in terms of dense, not dense, nowhere dense, what can you say? So let's begin asking, are the red points dense? Dense in M. Why not? Well, because there are plenty of black points that are not surrounded by, or not close to red points. Right? I can draw, let's say, a neighborhood here, and this guy is not next to a red point. So the red points are not dense in the space. So I can say the set is not dense. Can I conclude in this case that the set is nowhere dense? So they scream on the radio, Mayday, Mayday, the set is nowhere dense. What do they mean by that? The what? Yes, they're alone, right? But more specifically, what it means, right? They say we are not a dense, we are nowhere dense set. It means we are not capable of forming a defensive perimeter, right? So remember what is a nowhere dense set? It means that even if you include the limit points, so let's say whoever they can marshal, they can commandeer. You say you guy, you join our forces. Even then, they do not have a full neighborhood. Okay? So imagine they have this special glove, whatever zombie they touch will become a special forces soldier. Okay? Even if they had this situation, they are not capable of forming a full neighborhood, a full protective neighborhood. So nowhere dense set is one that's not capable of forming a full protective neighborhood. So the Russians in New York, let's go back to that example. Russians in New York, not a dense set. Why? Because there are plenty of people in New York that are not surrounded by Russians. You can go to different neighborhoods where there are few Russians, okay? But are they a nowhere dense set? No. Why? Because what they can do, they can just convert the entire Brighton neighborhood into a fully Russian one. Okay? Because they can convert every single person that's not Russian, make him Russian. Right? That's what nowhere dense set is one not capable of doing. The Germans, for example, no, they cannot do it because there are too few of them. where are we now? So, before I move on to the next topic, here is a question. I wonder if you can figure it out. Not right away, but I asked it already last time. Maybe I'll ask it on the final. So, question. Do there exist perfect subsets of R that contain no rational points? So what I mean is can you find a perfect subset P, which is a subset of R, such that P intersection Q is empty, and yet P is perfect? Okay, do you understand the question? So remember what perfect sets are. It's an exclusive club where every point in that club is a limit point of the club. So it could be of any side. So, and of course, I mean, some smartass might say, sure, P equal to the empty set. And that's true. But aside from this, that's what I'm asking. Okay? So if it's not empty, could you find a perfect subset of R? And I'm not sure, perhaps I should have been more careful. I'm not sure if you understood my claim. Every perfect non-empty subset of R must be uncountable. Not only is it has to be uncountable, right? But so think about it. So now we are talking about the Cantor set. So what you do is you take the interval from 0 to 1, and then you cut this interval into 3 parts, equal size. Okay, so this should be 1/3. This will be 2/3. And what you do is you delete the middle. You delete the middle thirds. So what you get is you delete the middle thirds here. set, so this we'll call the interval I0. This we'll call the level set I1. So what you have left are the intervals from 0 to 1/3 and from 2/3 to 1. And the next thing you do is, from each of those intervals, you delete the middle thirds. So the points that are deleted here, this begins with what? With 1/9. This is 2/9. This is 1/3. This one is 2/3. And then we have 4 it would be 7 nines, 8 nines, and 1, right? And you continue, so this is the second interval, and then you continue in this fashion. So you continue onwards. So the Cantor set, you take delta Cantor set, are the points that survive. So let's look at this. So let's ask a few questions. So question 1: do any points survive the process? So basically, the points that survive, I mean, you just take the intersection of the IN, that goes from 1 to infinity. Okay, and that will be the Cantor set. So you see what happens, right? So you begin with a full interval from 0 to 1, and the middle thirds are deleted. So no point in here survives the first deletion. And then I arrive into 2 islands. I have the left island and the right island, and then the middle thirds are deleted. Sorry again, the scale is bad, but you understand it's the middle third. And from each of them, now we have 2 intervals here, right? And anything between 1/9 to 2/9 has been removed. And similarly here we delete it, okay? Now the next process, you see what happens in the next process. A third of this length is deleted, and a third of that length is deleted. So this will generate 2, this will generate 2, this will generate 2, this will generate 2. Each of them is getting smaller. Do any point survive this process?
I'd say that only irrational points would survive because we're getting rid of.
And notice that we get rid of the open interval. This is closed. So we are getting rid of the open interval. So we are removing.
So 0 and 1 definitely survive.
Right. Removing open, middle, thirds, intervals. That's what we're doing. Okay, we're deleting the open middle thirds. Okay, so do any points survive the process? The answer is, as you mentioned, yes. We can see that 0, 1/3, 2/3, 1, and then we have 1/9, 2/9, what's it, 7/9, 8/9, etc. survive. because those points will never be touched, right? Deletion will happen from the middle, those points will never be touched. So in other words, those points are in the Cantor set, it's not empty. So the first thing I see is that the Cantor set is not empty. Okay? Now, let's try to say a little bit more about it. Notice that at each point in the deletion, I can say that, that either I can look into the left or the right interval, right? So I can say this is the left interval, this is the right interval. And then I look into this interval. What is this? This is left, left. And this is left, right. This is right, left. And right, right. Okay? And so the next intervals, basically all the points that get to survive to the third stage, they can be described by a sequence of 3 letters, left and right. Okay? So you can just make the following observation. Notice that that the points of delta are uniquely are described or can be described I should say uniquely by an infinite sequence of lefts and rights. Okay? So how do I know this? Let me just make a few observations. Okay? So what I can have is for each level set, so each level set basically the sets. So if I have let's say a sequence, let's say like this, left, 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 and then I go right. Let's actually just begin describing simply. Example. Let me try to describe what survives if I just have a sequence of left. Okay? A sequence of left translates to what? It translates to the interval from 0 to 1/3. So that means that the first thing that the point was it survived the first deletion and it ended up being on the left. Okay? And then I deleted another middle thirds and I took the left part. So I deleted another middle thirds and what do I get? I get 0 to 1/9. And then I deleted another middle thirds. What does it become? It becomes 0 to 1/27. Okay? And then the next is 0 to 1/3 to the power of 4, etc. Notice what is the length of those intervals. So you see we have a nested sequence of closed intervals. And what can we say about the length? We can say that length of 0 to 1/3 to the k approaches 0. So those points, basically in the sequence, if I just take left, 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 only one point can survive. You remember the nested interval theorem, right? So it tells you that if you take in R, closed, bounded, and nested sequences of intervals, then if I take the intersection of that nested sequence of intervals, I must remain with only one point. What is that point? So then, so basically, I can say that left, left, left. This corresponds to the intersection of the sets 0 to 1/3 to the power of k, where k goes from 1 to infinity, And what survives? 0. So you see this sequence, because the intervals grow to 0, so by the nested interval theorem, any nested sequence of closed bounded intervals, its intersection never empty. But even further, if the length of those intervals goes to 0, that intersection must be only one point. And what point survives? Obviously 0, because you take left, you see that 0 is ever present. So left, left, left corresponds to 0. What about, so tell me what is, if you understood it, what is left and then followed by a bunch of rights, by all rights? What is that going to be? If I take left and then followed by right, 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 you say with a bar. Bar means right repeats, so that corresponds to which point?
1/3k.
Right, so what you go is, you start here, you go left, and then you continue going right. What survives? If you continue going to the right, survives 1/3. You see, because right on the right, if you go right, 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 you only have 1/3 of it surviving. So that would be 1/3. Good? And why do I know that any sequence of lefts and rights will work? Notice, if I take left or right, I always move from the bigger interval to a smaller one. And you can see that on this level, so you can see that length of the interval here is 1/3. Length of the interval here is 1/9. This is 1/9, this is 1/9. You see, because this was 1/3, you divided it again by 3. So the level sets, each of them is of the same length. Let's say if I am at the level k, the length of each interval will be 1/3 to the power of k. So any sequence will work. You see why it's uniquely? Uniquely because when you go through lefts and rights, what you end up doing, if you go through left and right, you end up going through a nested sequence of intervals, which converges, the length of those intervals converges to 0, so therefore you end up going to one particular point. And therefore there is this correspondence. The infinite sequences of lefts and rights are uniquely identifying the points of the Cantor set. Each sequence, no matter how you take of left and right, it will identify a point in the interval. So that tells you something about the cardinality of the set. We're going to see that several times. Right, everybody, I am again loose here. You understand that every sequence of lefts and rights corresponds uniquely to a point in the interval. It is a code for a particular point in the interval. Because no matter how I decide to move, whatever sequence of left and rights I throw, I go down in a nested sequence of vanishing intervals. I go all the way down, and when I go all the way down, that's a point of a Cantor set. And I must converge to one particular point. So, what's the implication? Now, left and rights. Now, all this set of sequences of left and rights. So we can say this, right? So the cardinality of the Cantor set equals to the cardinality of infinite sequences of left, right. And what's that cardinality? That cardinality is, it's uncountable. That is the same as 2 to the power of, let's know if you remember that homework. Why? Because it's like attendance rosters. Instead of going left and right, let's say L is represented by 0 and R by 1. So if I take, so what is an infinite sequence here? An infinite sequence is like an attendance roster of zeros and ones. This is like the power set of the integers. Do you understand? No. So again, just recall. Let's say that that I had integer many students in this class. So there is student 1, there is student 2, there is student 3, there is student 4, there is student 5, etc. Okay. Now, some students come to the class, others don't. Okay. So look at it. So 1, 2, 3, 4, it's a sequence, and let's say what I represent. What with 1, let's say 1 I represent by 0, 2 I represent by 0, 3 is 1, 4 is 1, 5 is 0, etc. Right? What have I made? What sort of set does this generate? This corresponds to the set of the integers that does not contain 1, does not contain 3, but contains 3, contains 4, does not contain 5. Maybe contains 6, I do not know. Okay? So this is an attendance roster. You see it? Where is the 2 coming from? Attendance roster. Each of them has possibility either of getting 0, of being marked absent for the class, or getting 1, being marked present for the class. And a sequence of 0s and 1s identifies a particular day, a particular attendance roster. Yes? Now, what's going to be the representation? That's where we have the 2 to the power of aleph naught, right? So if I have, let's say, only 5 students, the sequences of 0s and 1s all the way to 5 generate how many possibilities? 2 possibilities for 1 times 2 possibilities for 2 times 2 possibilities for 3 times 2 possibilities for 4 times 2 possibilities for 5. Therefore, 2 to the 5. 2 to the cardinality of the set 1 through 5. What is aleph null? It's the cardinality of the natural number. So if I continue this analogy, then 2 to the power of the natural numbers will represent the set of attendance rosters for all natural numbers. Make sense? And this set is uncountable. How do we know it's uncountable? Very simply because there is a correspondence with the power set. Remember, according to Cantor's argument, if you take a set and then you take its power set, the cardinality of the power set always bigger. Remember that analogy with the chocolate, the French, right? So power set always bigger. So this is a natural number. This is the all natural numbers, and the sequences of 0s and 1s is like the same size as the power set of the natural numbers, which is bigger. Yes, please?
Shouldn't the Cantor set be smaller than Q? Like it should be a subset of Q.
No, it's not.
Why?
Because I'll show you. So right now you only see the endpoints, which are Q, right? So very good point, right? It seems to you that when I go left and right, I will only get rational numbers, but that's not going to be the case. That's good observation. Right? So I'm going to talk about it again and again, several times, but I hope that you understand what I mean. So first of all, you understand that using the nested interval theorem, I was able to identify each point of the Cantor set, not quite knowing what sort of point that is, with a sequence of left and rights. And if you prefer, you can replace sequence of left and right by just a sequence of 0s and 1s. Right? I'm not talking about how you write a number as a power series. I'm just talking about the representation. I'm giving each number in the Cantor set a unique address. Okay? And if I look at the address that I assign, it's left and right. That's the same as assigning attendance rosters, right? So a sequence. I just look at this. The first identification is by the nested interval theorem, and then I look what's the cardinality of that set by itself. So set of infinite sequences of 0 and 1 will be the same as the set of attendance rosters for a class that contains natural number many students. And the set of attendance rosters is the same as the power set of the natural numbers. And therefore the cardinality has to be bigger than countable. Therefore the Cantor set must contain points that are not rational. Otherwise it would not be possible.
Is the set of attendance roster a subset of the natural numbers?
No.
No?
No. No. The set of attendance rosters it's like the power set of natural numbers. It's like the set of all possible subsets. Maybe that's what you meant.
So like if you expand the set of attendance roster, wouldn't you get just natural numbers?
No, I get sub-collection of natural numbers. So for example, let's say that my sequence is this. Let's say that my sequence. So this is the set. Let me just erase this example. So I have 1, 4, 5, 6, 7, etc. And let's say that what I observe is this is 1, and everything else is 0. So 0. Okay, it's going to be 0 bar everywhere else. Okay. What does this correspond to? If you understand how it relates to the power set, what sort of subset of the natural numbers is it? What happened here? I selected a particular sequence of zeros and ones. In this case, zeros everywhere except at 3. What happened in this class today? Only person that I designated by 3 came. So this is a singleton subset. Okay. You follow? Right? So each attendance roster I can translate to a particular subset of the natural numbers. And there is a one-to-one correspondence. Yep.
So wait, I have another question about Cantor. Does the Cantor set just contain like all the end results, or does it also contain like all the intervals that precede it? So like
Only the end results, because the Cantor set is the intersection, right? And if you take the intersection, because the sets get smaller, it's the same as going down the ladder.
So like L and R aren't in the Cantor set then?
L and R are not representing, they represent only interval, okay? So notice the way I describe the Cantor set is that you have to write a sentence using L and R, and the sentence has to be infinite in length. LR, and let's say LR, 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 if I do this forever, that will identify a unique point in the Cantor set. But if I stop, that only identifies an interval. I don't go all the way down. The interval will not fully survive.
But then how could you get irrational numbers from that?
Irrational?
Yeah.
You will see. You will see. We will get a particular representation. We will select a convenient base, and in that base we will represent the Cantor set. And you will see that the numbers, that you get irrational numbers. One easy way to do that, I suppose, just make sure that the sequence of L and R are erratic. Don't follow a pattern. If you go LR, 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 that is a rational number, right? But if you go L, 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 R, 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 basically what you do is, let's say you begin 1 L, then R, then 2 L's, then R, then 3 L's, then R, then 4 L's, then R. That would be an irrational number. Because you behave in a non-repeating pattern. Okay, but again, we will see more precisely. We will get another language to describe the points of the Cantor set, another way of addressing those points, and we will see that we have irrational numbers. But it's clear, if you believe this argument, it must contain many irrational numbers.
I believe that argument, but
But I just drew. So what I wrote here are only the endpoints. Okay, only the endpoints.
picture irrational numbers like coming from that.
You will see. Not only will you picture, you will actually write which numbers are in the Cantor set and not.
I mean, as a power series, the number would be.
We will figure a procedure for it. All right. Have a good one.
I feel like